in principle, we can start from the very beginning, which.
Okay, so hi everyone. We have not met, but so my name is Sebastian Wetzel. Hi everyone online. Hi Julian. I saw you online. So thanks for the invitation. Thanks for that we were finally able to meet in person. It's really great, and the weather is also quite nice. I appreciate a lot the work that you put in this workshop, because I know when I travel. During these times, it's quite hard, and I can only imagine how hard this is for all the organizers in the organizing team to put this workshop together. So another thing that I appreciate a lot is that this field of machine learning in physics, in theoretical physics, which is very non-conventional compared to what machine learning was when the big boom with the ImageNet started. That this is now finally a field and is recognized as a real scientific discipline. So let's get to my talk. So I'm going to talk about interpreting artificial neural networks in the context of theoretical physics. So let's have a very quick overview. So we've all heard from the previous talk from Marco and in all these news articles of all these cool successes of artificial neural networks in all these different disciplines. And the main one that started the hype among artificial neural networks was the convolutional neural network, especially in 2012 when the AlexNet won an image classification competition and outperformed all other algorithms that were state of the art at that time. And since then, it has been, neural networks have become popular in many different applications. So for example, the autoencoder in generative modeling and anomaly detection, or the Siamese network in similarity detection. So you've already heard about the autoencoder from Marco. And so I'm also going to explain something at the autoencoder, which is quite similar to Marco. And we will also talk about one network that is not very much known, but in my opinion, it has so much potential. It is so powerful, which is the Siamese network for similarity detection. So just a quick word. So what does this Siamese network for similarity detection do? So instead of like telling you what kind of class one certain input is, like a convolutional neural network in, wait, I can use this mouse, right? Okay, that's cool. So like in the convolutional neural network, where the neural network assigns a certain label to the image, or in the autoencoder, where the autoencoder tries to reproduce the image, and we're interested in this latent space. The Siamese network, the network tries to predict if these two pictures are the same picture. So what does it do in this case? If these two networks are identical, these pictures get mapped into a latent space, and then there's some other architecture or a neural network, and it will then determine if these are similar or different. So what are we dealing here in this talk? So when we talk about machine learning, very broadly, machine learning is the subfield of computer science that gives computers the ability to learn without being explicitly programmed. So in a very broad setting, we assume here we have training data. Here in this case, we have cats and dog images, and then we have this black box algorithm here, an artificial neural network, which is widely accepted as being one of the, or if not the most black box machine learning algorithm that exists, but also the most powerful. And this algorithm is then somehow trained to figure out what are cats, what are dogs, and if it gets an image where it does not know the label, it will, after it has successfully been trained, correctly output that this is a dog image. And now the question that that I try to answer, not in the context of cats and dogs, but in the context of theoretical physics, is what does this neural network actually learn? And The other question is, can this knowledge, if we figure out what the neural network has learned, help us in some sense in scientific discovery? Oh, just, is there a clock somewhere? No, no, okay. I will get the time really wrong.
The computer gives the wrong time as well.
Yeah. Yeah.
It's 11.
Yeah. Okay, we'll use this one. Okay, so these are the questions we want to address in this talk. And what is really cool about this is we could not answer this question if we would be dealing with cats or dogs, but we have some advantages in physics that computer scientists in the cats and dogs discipline do not have. In physics, we can formulate, or our quantities that we're interested are formulated in equations. So let's think of the energies or order parameters or conserved quantities or whatever you think of is formulated in equations. These are the objects that we deal with. If we think about cats and dogs, even if we would find an equation of a cat or dog, we would not understand what is a cat or dog from the equation. So it's like we have a huge advantage in understanding what these neural networks do, because neural networks are written in the form of equations, and the objects that we want to extract are also written in the form of equations. So this is the introduction of my talk. So the outline is, I'm briefly going to mention, since it's the second talk, I was also prepared to talk a bit more about what are artificial neural networks. Then I'm going to mention some interpretation techniques, some which are already known from the computer science side, and others which are specific to the natural sciences or to physics, which we use in order to find all these concepts, physical concepts in these networks. Okay, so first step, artificial neural networks. So artificial neural networks, I hope everyone knows it, but let's just recap of it. So artificial neural networks are just this directed graph that gets an input value, feeds the input values through all these hidden layers, and then gives you some output. Each of these nodes in this graph is a perceptron, where it gets an input x1, 2, 3, multiplies it by some weights, adds some bias, puts it through some activation function, and then gives you an output y. In a typical neural network, there are millions of these perceptrons, and through the universal approximation theorem, we also know that the neural network with a certain number of hidden layers and hidden layers and weights and perceptrons in each layer can approximate every function under certain conditions to an arbitrary degree. We also talk about input data, which is a data set denoted by capital X with feature vectors on each data point x1 to xn. Each of them has a label. And we want that the neural network, big F, if we apply it to the data set, gives a prediction y, which is as close as possible to the true prediction y. And this should not only hold on the training data set, but also generalize to some unknown test set. And how do we do this? We adjust these weights and biases via backpropagation and gradient descent normally, such that the function f, which denotes the neural network, comes as close as possible to satisfying this condition. Okay, so we will also need to remember this structure when we interpret the neural network again. So let's talk about interpretation techniques. So what I'm going to talk about are the interpretation techniques of bottleneck interpretation together with the correlation probing neural network. But first, let's talk about some other interpretation techniques that are commonly used, and some of them work and some of them are a bit harder to make them work, and some of them do not work so well. Okay, so the first thing that one can do when one wants to interpret neural networks is you look at the weights. So you train your neural network, and then you look at these weights and biases, W and B, and normally you have millions of them. Sometimes you have a very small network where you only have a few of them. If you have a few, sometimes it makes sense to infer some of these, some quantity from these weights. But if you have millions of them and you have no special structure that you can abuse, then it's normally not very handy to look at the weights and infer some quantities. It can be done in simple problems, but in most of these cases not. If you have convolutional neural networks and you have a very special structure in the input, or if you did some feature engineering before, it can work if you just concentrate on the input features or the first layer of the neural network. Another thing is influence functions, which is also quite a neat technique. So what is the idea behind influence functions? So you train a neural network or whatever machine learning algorithm you have, and then you want to see what specific input, which can be either a training data point or it could be a feature in your input data, is responsible for a certain prediction or responsible for a good performance of the machine learning algorithm. So what you can do is you remove these specific data points or features and measure the effect on the performance of the neural network. So it can be a change in the loss function, it can be a change in the final loss, it can be a change in the prediction that it makes. You infer that the largest change in the performance indicates the most influential data point or feature. Okay, let's imagine how could that be. For example, what could happen? For example, if you if we look back at the cats and dogs problem, classification problem, it could be that the eyes or the nose or the fur is important. So let's say the nose is important, then you remove the nose on each picture. If the classification performance drops a lot, then you know that one of the dominant features that the neural network would have used for classification would rely on the information that is contained in the nose. Okay, let's go to more physical examples. So this is a very famous paper right now. These people have simulated dark matter and used graph neural networks to map the so they mapped the simulation onto a graph neural network, and this graph neural network was then learned the force equations that govern the movement of the system, and then they interpreted the output of the graph neural network, and they could recover then, with the help of symbolic regression, the underlying force equation of this dark matter system. So don't ask me too much because I don't understand too much what was going on. Another system that is also quite similar to our interpretation method is this correlated convolutional neural network, which was here applied at the condensed matter system. And what they do, this network has different input features in the first layer, which are constructed to mimic certain correlations that can be present in a condensed matter system. And then they train the neural network, and then they check which of these input features gets activated. So which has a strong coefficient in front of these input features. And so they deduce which of these input features or correlations are important for a certain prediction of the neural network. And another paper that is quite similar in spirit to what we do is about discovering physical concepts with neural networks. This is also a paper that relies on an autoencoder. And what they do, in addition to training an autoencoder on some kind of physical system, they attach another neural network to the latent space. And this neural network needs to be able to make some certain predictions or ask certain questions. And it turns out that this then helps in finding a suitable latent representation that is perfectly aimed at answering a certain question on a physical system. Okay, so now I give you like a quick overview about some examples. I didn't mention all of them, just that were some that were like striking to me or pretty famous right now, that were also in the same spirit as what I'm doing. And so in the following, I'm going to talk about the concept of the bottleneck interpretation and the correlation probing neural network. Okay, let's talk about the bottleneck interpretation. So normally, interpretation of neural networks is really difficult because the information. So I already told you, and you all know. I'm sure you know it if you tried it. There are so many neurons in a neural network, and there are so many weights, and all the information gets spread out among them, and the architecture of a neural network is not really suited to be read out, because with all these activation functions and these linear transformation, it's not really natural to find physics equations in there. So if you imagine, let's say you have a ReLU activation function, which is just a piecewise linear function, and these and weight matrices, then all the functions that you can reproduce are piecewise linear functions. But of course, we have the universal approximation theorem that allows us to approximate every single function to an arbitrary degree. However, this piecewise linear function is naturally not in the form of a physics equation. So if there would be a sine function in this piecewise linear function, it would be really inconvenient to extract. Or if there would be something even more complicated, how should we find it? And now the idea with the bottleneck interpretation is, instead of looking at this whole neural network, we look at specific parts of the neural network. So we either look at, okay, where has the neural network a very compressed form, like in Marco's case with the autoencoder and the bottleneck, we have a very compressed form, or the output itself, if you have a binary classification problem, it's just one neuron, there we have a bottleneck. And the idea is then, if the neural network needs one certain important quantity to make a prediction, then this information needs to be contained in the bottleneck. So if the neuron contains the information of one single quantity or observable, there must be some kind of mapping between the output of that neuron via a bijective function to this observable. So in order to practically use this idea, we want to enforce bottleneck or identify bottlenecks where we can check for the information contained in a single neuron. And then when we have that, in order to extract that information or that quantity, we want to perform some kind of regression. It can be symbolic regression. In our case, in most of the cases, a standard polynomial regression was enough to already retrieve many physical quantities. Okay, let's look at one of the first examples that was popular in theoretical physics. So this method is using convolutional neural networks to find phase transitions, which was first introduced by Juan, who is also giving a talk later. Maybe he's already here. Hi, Juan. And the idea is here, you produce a lot of Monte Carlo samples, in this case of the Ising model in 2 dimensions, where, as we know from Marco's talk, we have a phase transition at 2.269. And we assume that we know that there is a phase transition somewhere, but we do not know where the phase transition is. So what you do with your training data, so you have produced Monte Carlo data everywhere on the whole temperature axis. You prepare your training data such that you label low temperature configurations up to a certain temperatures where you are certain that you're in one phase with label phase A, and with other configurations where you're certain that you're in the other phase. It could be at infinite temperature, or it could be lower, and you label them with phase B, but you do not label the samples in between. And what you do, you train your neural network to predict the phases, and after you have successfully trained, you infer the phases in this intermediate regime. And you will then be able to predict the phase transition very accurately to a very high degree of accuracy, around true phase transition 2.269. And now the question is, what has this neural network learned to infer this prediction? So we could, okay, at this example, it might look like a stupid question because we know all of this. But if we imagine someone would write a paper about a new physical system, and he would propose this kind of a phase transition. Now the problem is we suffer a lot from this publication bias, that some things get published, some things that don't get published. If we don't know what these neural networks learn, you don't really know if the prediction is something that is meaningful or not. If you're experienced with neural networks, you might even reproduce this curve, even though your neural network does not really learn the correct underlying quantities that you want to learn. It could learn something like the temperatures and find some kind of interpolation between these two regimes. Could be it learns some kind of fluctuations, and it would see that at higher temperatures the fluctuations are larger than at lower temperatures. But in fact, what happens that in these cases, neural networks will learn some physical quantities. Okay, let's wait a few seconds, and then I will tell you what these physical quantities most of the times are if it's trained successfully. Okay, so how do we interpret this neural network? So with this bottleneck interpretation technique, we need to look, okay, is there some kind of bottleneck, or do we need to enforce a bottleneck? And in this case, a very natural bottleneck in a binary classification problem, it's just at the output. Now we have a problem that at the input, we normally have way too many features, can be hundreds or thousands. If you now want to figure out the relationship between the output and the inputs, that is normally still quite hard, and you couldn't really apply regression in a feasible manner. So the idea here is the next step, which is this correlation probing neural network, is to reduce the number of input features that you use for your regression step, which then helps to interpret what the bottleneck at the output has learned. And the idea is here, you train your neural network, and then you reduce the capacity of the neural network to learn all functions. So you cut a few connections, or you introduce some kind of layers which deny the neural network to learn all the functions that it could normally learn via the universal approximation theorem. So, for example, if we look at this image, so this image is a spin configuration, and a normal neural network can learn all correlations among all different spins. We can now deny the neural network by cutting some connections to learn some of these correlations between spins. So for example, if we reduce this receptive field size of these neurons, and then we average later, after the neural network can only learn correlations in a smaller receptive field size, this neural network cannot learn any longer range correlations in these functions, in the functions, in the features that it wants to learn. So the idea is here. We start with a huge neural network that can learn all the functions. Then we reduce the capacity of the neural network such that it step by step, it can learn fewer and fewer and fewer functions to make its prediction. And at one point, the neural network will observe a drop in performance. Sometimes it's a smooth drop, sometimes it's a sharp drop. But if it's a sharp drop, then you cut one connection too many. You lost one information that was important for the neural network to make its prediction. And at that point, you have inferred one. So you start at inferring properties about the most dominant feature that the neural network has learned to make its prediction. And if you do that from different angles, so for example, one was this introducing this averaging layer, and one was the reduction of these receptive field size of all the functions that a neural network can learn. Then you see in the case of the Ising model that this can help to reduce the regression problem that you need to solve in order to interpret what the neural network has learned to a very simple one. So this is the interpretation of the convolutional neural network that performs face recognition on the Ising model. And you see, if you start with these receptive field sizes that can on 20 times 28 lattice size, and you train your neural network, you end up with a loss at almost 0. If you now reduce what the neural network can learn, so in this case, we only see these 4 examples, then you can reduce it to a 1 times 2 receptive field size, and the loss is almost 0. So at that step, the neural network still learns everything that is necessary to correctly classify the input samples. And if you go lower, the neural network loses some kind of important information. It makes still a good prediction, but it has already lost some dominant features that it cannot use to make its prediction. So we know the neural network needs to learn some kind of correlation to make a perfect prediction, some kind of correlation with its neighbors. And if you go there, the self correlation also gives you some information, but if you lose that, you get to the baseline, and you can't learn anything anymore. So this loss is just in a binary cross entropy. This is what you get when you just randomly assign labels with a probability of 0.5. Okay, let's look at what do these 2 receptive field size correspond to. One, so receptive field size of 1 times 1 can be corresponds to this function. I forgot to talk about the regression step, but in this case, it's really easy because if you perform a Taylor expansion of a function that only has discrete values as arguments, like 0 or 1s, 0 squared is 0, 1 times 1 is 1. So you reduce, in a Taylor expansion, you reduce the higher order terms to the lower order terms. And so your regression problem becomes so easy that you don't even need to do the regression anymore. So you only need to do a very, very simple regression task, and you will find that the first that this receptive field size neural network has as a dominant quantity extracts this dominant quantity from its samples to infer the prediction, and this quantity is known as the magnetization. And the same can be done with this receptive field size. We can again do think about the Taylor expansion. We only have a very few terms. Then you perform regression, which you don't really need to because there are only so few terms. Biases and weights can be observed, can be thought of belonging to the neural network itself and can be absorbed there. So the only quantity you have left is the expected energy per spin side. Or if we want to be even more strict, the minimal quantity is just so instead of having correlations in all directions, it is enough to have just 1/4 of the energy, because we have restricted ourselves to only using one kind of neighbor each time. But it's still the same quantity. And you can plot these correlation plots between the latent prediction So this psi belongs to here, as long as we do not know what Q of S is, and the norm of average spins, or the average product of neighbors, and you see this is a perfect correlation. It's not linear, it doesn't need to be, but it's a perfect correlation between these two. Okay, so we conclude. So in these cases, the neural network has found the energy and the magnetization to deduce its prediction. And we can now take this a step further and do the same thing in lattice gauge theory. Okay, so in this case, we have SU2 lattice gauge theory, not SU3. I'm sure you know much more about this than me. There was a fun little project because at that point, I asked Manuel Scherzer, can you give me some more complicated Monte Carlo configurations where I can test my interpretation model, and don't tell me what's going on, because then I would be biased and I want to be blind. And so that's why I did at that point not know too much about lattice gauge theory, and he helped me out with these configurations. He sampled it with the Wilson action, performed these Monte Carlo samples. We did the exact same phase classification analysis as with the Ising model. We found a phase transition very close to what, so the green and the blue ones are neural networks. The red one is what you get if you just calculate the Polyakov loop on the lattice sides. And so the neural network finds a very accurate phase boundary. And now the question is, can we do the same thing of interpreting the neural network as we did in the Ising model? And so we can do that again. So we start with the full lattice size, full receptive field size. The neural network can learn all possible correlations on that on the Monte Carlo configurations. Then we lower the capacity of the neural network. You can learn less and less and less. And what we then find, we cannot reduce the receptive field size of the neural network down to 0, because in the Polyakov loop needs spans over the whole time direction. So the neural, when we do this interpretation techniques, we find that as soon as we reduce the receptive field size in time direction, the neural network cannot learn anything anymore. It's also important to note our time direction is only 2. So we have a lattice of 2 times 8 times 8 times 8. And if what? Yeah. Okay. So so we have now reduced the neural network. We check what the neural network has learned. We perform now a real regression analysis, and we find that the neural network learns exactly the equation of the Polyakov loop to make its prediction of a phase transition. Okay. So this ends the first part of this interpretation. Technique.
2 questions.
Yeah.
So the first one is about the previous slide, I think. So the position of the transition.
Like
transition.
this
Yeah.
one. Yeah.
So this is obviously on the data you analyze is on a very small lattice.
Yeah.
And the dashed line, is that on the same lattice? Or?
It's the same lattice, but it was evaluating the Polyakov loop just by hand.
But in principle, in the infinite volume limit, they may agree even better, but you can't test that.
So the thing is, in the infinite volume limit, neural network will have a lot of difficulties to figure that out.
Okay.
So, if we want to get more into detail, maybe there are some of you have tried training on some gauge configurations, and neural networks have a very hard time to figuring out all these gauge features, like all the loops on these plaquettes. So the longer, so for example, if you go to the infinite time limit, or if you extend the time dimension, even if you just extend it to 4, the neural network would have a really hard time to learn what is going on.
The second question on the next slide.
This one?
So a way to reformulate it is to say that the method you use actually identifies what the order parameter is.
Yeah.
And so what if there is then, say, no order parameter? Say if it's a crossover, there's no exact symmetry. But would it still work like you know, as beautiful as this? Or
It's a tough question, and we talk a lot about this. And you can answer. So I can give you a quick answer is like, okay, if we work in these small lattices, then everything that we look at looks like a crossover, because you need to go to an infinite volume limit to have a proper phase transition. That is a quick and dirty answer, but we have had many more discussion about it, and it's so as far as for me, it's not quite resolved.
that's a good point.
So you cannot.
Yeah, but then you could say it's even then more surprising that it finds the Polynomial loop as the all parameter, with only n tau equals 2. So then,
Yeah.
So to revert the argument, then that is
Yeah.
even more surprising. Okay, thanks.
That's good.
Yeah.
Yeah, so I was a little bit curious as to how the transition temperature was identified for these networks if you're only training in the very far in the symmetric phase and very far in the broken symmetry phase. I can imagine, I mean, you mentioned that this bottleneck should learn a quantity or maybe some bijective function of the quantity. And
Yeah.
could that function push around where that transition actually is placed, where the 50% line is placed?
Okay. There are a lot of details. So I don't know on what level you're asking that question. So
I just need to say, was it sort of, is it natural that your net should find the transition temperature where it is, or that you should just get some?
I think so. We don't even need to go to the SU2 gauge theory. We can talk about the Ising model.
Yeah, you
imagine that. So it's like, I think at the beginning it was really surprising that it works, because so as far as I know, this was the first, like Juan's paper was the first neural network paper that did something. If you just look at it from a computer science perspective, it does not necessarily need to work. It is very surprising that the neural network learns something. So you only do this. You only do phase classification. You only classify phases. It is not in some certain region. It's not clear that the neural network learns an order parameter or something like this, or it's not even. It is even less clear that the neural network like puts the right threshold at the order parameter to infer its predictions. So it is a bit surprising that it works out. And the best argument that I can give you is empirically that there are so many papers who have reproduced accurate phase transitions with this. So when I say I interpret these neural networks and I tell you that these networks learn the order parameters, there's still the open question: why is the bias term at the exact right level to give you the exact to give you the correct phase transition temperature? Yeah.
Question online.
Yeah. So
Can I ask another?
sure, Parag, go ahead and then Feng.
Okay, sure, thanks. So I'm interested in the fact that this is, I mean, the SU2 is a gauge theory, while this Ising model is not. Did you have any, I mean, takeaway messages from that? How was it more difficult to train the model?
Oh yeah,
So
on gauge theories, it's a lot more difficult to train. So I can imagine if you go to a larger lattice size, then the neural network would also learn some kind of action or energy. So it will learn loops on the plaquettes, which means it has to multiply at least 4 matrices, and that is exactly the point where if we went to an extent of 4 lattice sites in time directions, our neural network was not powerful enough anymore to learn what was going on. So 2 or 3 lattice sites in time directions, that is everything we could handle. Yep. Thanks.
Okay.
Okay, can I go? Oh,
we have 2 more questions.
Oh,
So Feng and then Alberto. Feng, ask your question.
Oh,
Okay.
could you comment about the more scattering in 2 times H? Like the bigger network has more scattering. Seems like it's working hard. It's working worse than the simpler network. Could you
wait,
comment?
you mean the scattering here,
Yeah.
like in this correlation plot? Okay.
Yeah.
So first about these correlation plots. So it's like these correlation plots are, so it's like you plot the output of a certain configuration of the neural network, and you compare it to the exact value of here, the Polynomial loop. So when you have a correlation plot that is like this, and you have, I don't know how many points we have, between 5 and 50,000 points in there. So this is a very, very, very strong correlation, and a very strong correlation plot that tells you the correlation between these two. That is a lot stronger than if you do some temperature averaging. But of course, the neural network in this 2 times 8 times 8 times 8 model has more weights and biases that need to be adjusted than the reduced model. So you have a bit more scattering than in the final model. So the neural network. Okay.
I see. Thanks.
Okay. And which was the other question, Ricardo? Have you used?
Yes, can you hear me?
What? No, I did not. But you might tell me more about it.
Yeah. Can you hear me?
Yeah.
Yeah, the point was that what you told us now, I think it's a bit impressive, because inside the latent space, you can get some variables that are informative, that has a physical sense. That is, I think, a bit impressive. And but the usual computer scientists, to explain a neural network, they use techniques like what I wrote in the chat, like sharp of deplete, that highlight the input, highlight, for example, the pixels, highlight the what input is important to have that prediction. But in this case, is how to join the input information with, for example, here the Polyakov loop L. I mean, we leverage the fact that we know the physics, but if we start from scratch, then we are maybe lost.
So yeah, what did I leverage? I leveraged that we deal with some thermodynamic or extensive or intensive quantity, because that allowed me to use this averaging layer and reducing the receptive field size to learn correlations in a small part of the image. So that's what I used to the SAHP and deep lift. So the thing is, when I started this, of course, at first I was looking how to interpret the neural network the same way as computer scientists do. But then I did not go over all of these techniques, and I don't even know most of them. But what led me to do it the way I did was, even if I would have gotten an answer from these interpretation techniques, they would not have told me the answer that I like. And I'm only able to extract some kind of dominant quantity. And then, but if you look at it from another perspective, if I would get like hundreds of or even tens of dominant quantities, I would still, these would not be, I would not be able to make sense of them. So my method has limits, but on the other hand, the limits of my methods are exactly in the way that I want them, because only then I will be able to understand what my interpretation technique tells me about it. So maybe you could tell me at one point more about SAHP or deep lift, because I don't know it. But the methods I know did not yield an equation in the form that I would be able to understand. Okay.
Yes, and maybe if I can, another question that rise up. And what if the latent prediction is more than one dimension? I mean, 3 dimensions, and maybe I recognize 2 of these dimensions as physical quantities, and the third maybe I don't know what it is. What I should do to understand what that quantity is? I mean,
Wait, so if you have more than just one bottleneck neuron.
Yes.
So it gets harder, and okay, there are different levels to the questions. So you can start with, you don't know what the correct number of bottleneck neurons is. So in the case of a binary classification problem, it makes sense to have just one. But if you look at the autoencoder, you don't really know what you should choose to make that to make it happen. Or you can even think about what we will talk later about our examples. So you can do different things. So you can start with some kind of so the simplest thing is you train different architectures and you look at what is with what neuron do you still achieve a low loss, but has also a low number of, so it's like you reduce the number of neurons and you still want to achieve a low loss in the same spirit that we already did. And the other way could be you use a L1 penalty while training. So the neural network decides after choosing the L1 hyperparameter correctly to choose the correct number of latent neurons to represent your output. And what happens, but I'm not very good at it, some people claim they can properly decouple the quantities in these two neurons, and that is a big problem. So if you have a higher dimensional quantity like an order parameter in the XY XY model in 3 dimensions, that is something natural that you can interpret. But if you have 2 different quantities that need to be encoded in these 2 neurons, it will be a mess. So you don't even need to have millions of neurons. If you just have 2 and they get entangled somehow, it can already get really hard to interpret. So if you have the luxury to only have 1 single bottleneck neuron, stuff becomes a lot easier. Okay, did that answer somehow your question? I hope.
Yeah. Thank you very much.
Okay, can I go on? What is the time?
Well, I mean, you're late, but it's fine.
Okay, I have so
The main thing here is to discuss. So.
okay, I have a lot more. Okay, but I think I can skip a lot of the autoencoder part because Marco already talked about it. So in this case, we train the autoencoder to reconstruct an input sample. We minimize the reconstruction error. In this case, instead of training just at certain temperatures, like Juan did in low and high temperatures, where we know the phases, or Marco in his infinite temperature limit, we train on all of them. And we find that in this case, if we interpret the magnetization if we interpret the latent space, we find it's perfectly correlated with the magnetization. So this is a correlation plot, and so this correlation plot is a lot stronger than such a temperature average plot, because you could get a similar plot with if the neural network will learn the energy, but the correlation plot would be a mess, a complete mess. So this correlation plot is a very, very strong indicator of what the neural network has learned. One more comment: if you do this, for example, with the anti-ferromagnetic Ising model, you would find that the latent parameter is perfectly correlated with the staggered magnetization. And it seems like from our discussion, in order to achieve that, you would need to train on all configurations, and that's probably the difference, I think, but we can discuss later. Okay, so then we can skip over the autoencoder and we go straight to the Siamese neural network part. So the Siamese neural networks are not so well known, but what do? They take 2 inputs, they put them through 2 identical networks and map the input to some latent representation. And after that, they get fed into some kind of comparison neural network and put into some kind of loss function. In our case, we use a binary cross entropy loss. And we have a network bottleneck here that we can interpret. Let me just give you an example of what these Siamese neural networks do and why they're important. Okay, so if we do classification in machine learning, we imagine we have a multi-class classification problem. Here in this case, we have my group in Canada, and some of these people already left, which is important for the example. And we already got some new people, which is also important for the example. So we have 4 different classes of pictures of 4 different people. We train a machine learning algorithm, and this machine learning algorithm will be able to tell you to which person this picture belongs. Now, let's imagine there are new people coming to the group and other people leaving the group. So instead of having just 4 classes, we can in principle have infinitely many classes, like new people coming, new people leaving, old people leaving. You can repeat the process infinitely many times. So what you can do, you can train each time a new model, or you can use a Siamese neural network. And what you do is you as an input, you take these pairs of pictures and you train the Siamese neural network to predict, are they the same person, the different person, or are they the same person? And what is now cool is when a new person comes in and you have a reference picture, this neural network will be able to, if it's correctly trained, to assign the correct label, so same in this case, to this image pair, even though this person was not in the training data set. So I think now you can understand why I think this is really powerful, and there's so much low-hanging fruit. So let's go to apply this to some very simple physics problem. Let's imagine we look at the solar system in 2 dimensions. We have the sun, we have hundreds of planets flying around the sun. In our case, I think we had 10,000 planets as training data flying around the sun, and we measure the positions and the velocities in one night, and we measure the positions and the velocities in another night. And there are some astronomers who could label this correctly, so they could say, okay, this is the planet that we had from the night before, and they can identify these. So this gives us the labeled training data. But now there are a lot of remaining planets left where we cannot assign which planet corresponds to the other planet in the other night. And so we train a neural network on our training data, and we train on these pairs, positions and velocities corresponding to observations of the same and different planets in the night sky. So it's important to have a balanced data set, same number of balanced and same number of same and different labeled pairs. And if you now apply this Siamese network to predict if 2 planets are the same, where you did not know if they are the same, you see that has a very high accuracy of 98% in training, 97% in testing. And we can now look at this. I can show you again. This natural bottleneck neuron, we only have 1 in this case. And we can interpret it. Now we need to solve a proper regression task. And we find that we have only 2 dominant contributions. They can be seen as a prefactor. We have set the mass is equal for all of these planets. Otherwise, the problem would be more simple. We find that this latent representation is the Z component of the angular momentum. And we can also plot this perfect correlation plot of tens of thousands of points. In this case, I showed you another quantity that the neural network could have learned as a conserved quantity, which would be the energy. And we see that the correlation plot looks like a mess. So we can deduce here the neural network has learned the angular momentum to infer its prediction. Okay, one more example, and then we're done. We can do the same thing with Lorentz transformations of electromagnetic fields. So we have 2 observers. They can observe the same or a different electromagnetic field configuration. For some of them, they're known which are same, which are different. Some of them they don't. And we can perform the same analysis. And we interpret, so the Siamese neural network is able to correctly infer which electromagnetic field configuration corresponds to each other. We can interpret what the neural network has learned. And we see here, it has learned the determinant of the field strength tensor as an invariant of the Lorentz transformation to infer its prediction. So this would also be another invariant, which it does not learn in this case. And here we have, again, a perfect correlation. So am I now over time?
Well, I mean,
Yeah.
Time is relative.
yeah,
Okay.
you ran out of time. So
Okay, I'm so over time.
Please go
Okay,
ahead.
sorry. That was not my intention. Okay, so the summary is interpretation of neural networks is hard because all this information gets distributed among so many layers and so many neurons. So the idea is like to bring this back home, make everything small, compress the information through some bottlenecks at two parts. One is at the part where you want to have your input variables for your interpretation procedure, and one is at the part of the neural network where you're interested in what is going on. And if you do that properly, you can use regression to get an explicit expression of the single most dominant quantity that the neural network has learned to infer its prediction. And the neural networks applied to face recognition to learn order parameters, or energies, and Siamese neural networks for similarity detection, learn invariants or conserved quantities. Okay, so thanks for your attention.
Thanks a lot, Sebastian. Maybe you can take a couple of questions.
It's a curiosity more than anything else. I mean, when we are describing orbits in classical mechanics, a quantity that plays a major role is the length vector. So now the question is, wouldn't you have expected your Siamese network to learn the length vectors if you're comparing planets rather than the angular momentum?
Yeah. So we checked for this length vector. Yeah, we checked for that and it didn't learn it. And so I don't remember everything that we thought about it. Maybe you know more about it. I think there's some transformation of some. So it's not an independent conserved quantity, but it's like it can be constructed from other conserved quantities. So it's like if the neural network can. So it's like if the neural network can learn a conserved quantity that is simpler, why would it use much more capacity to learn something that is more complicated? And I think this is something that in general goes on in neural networks. But I do not know. This is what I think, and how I would explain it, that the neural network learns simpler quantities first, but this is not a definite answer.
Okay.
Yeah, I just have a practical question, maybe on your previous slide, or maybe on the angular momentum slide, or this one even. Yeah. So polynomial regression. So what is it? So how is the input variables are E and D, say, or how does it work? How do you know?
Okay, so polynomial regression is linear regression with polynomial features.
But how do you know? So why E and why do E1, E2, E1, E2 appear here? Because they are the inputs.
So it's like our electromagnetic field configurations are just characterized by these 6 numbers. So it's like the input variables of the polynomial regression are these features. And what you do then, so you start with features of order or degree 1. So it's like just linear combinations of these, and you perform a linear regression, and then you see, can my linear regression reproduce the output of the neural network in a linear? So it's like you need to linearize. So the detail is a bit more complicated because the neural network learns weird functions of what is going on. So you need to do some linearization. But in essence, you build features of the lowest order, check if your regression is accurate to reproduce what the neural network has learned. Then you go 1 order higher, check if the regression is able to reproduce it. If not, you go 1 order higher. You do this for a few steps, and normally you see, or in our cases, we saw that after 2nd order, we can truncate, and it's enough to figure out what it has learned. Sometimes. Okay, so I just want to give you an example about the energy, for example, here. So if you fix the angular momentum, do the same analysis again, then the Siamese network learns the energy. If you want to do the interpretation, then if you just do polynomial regression, it will fail. It will just look like a mess. It will not even look like a proper Taylor expansion. But if you, in this case, you can either supply the correct terms to your linear regression, which we did in this case. We supplied a few more terms, and they were enough to be able to reproduce the energy. But if you do not know which terms make sense, you need to go to symbolic regression, and then it gets harder. But I talked about this graph neural network interpretation with in the dark matter system. They used symbolic regression.
Because what I'm wondering about is you have to get the right variable to express this in. So this is second order polynomial in E and B. If you would have taken some, if your input variables would be some power of E and B, it just works out. The same with angular momentum, say position and velocity. Or if you include different mass, position and momentum. Then it would be a nice second order. Because they fit in the right way.
Exactly.
If it would be unlucky, you would never be able to get it, or it would be kind of a funny polynomial.
So you're right. So it's like what can happen is like in physics we're often interested in some certain limits and some the equations that tell us the most about these physical systems are normally quite short. There are some kind of approximations or sometimes first order perturbation theory or whatever that tell you the information about these systems. And all these more complicated equations are normally also quite hard for us humans to understand. So while it is true that it would be harder for us to find more complicated expressions, it is also if the interpretation procedure would be able to extract more complicated equations that are way too complicated for us to understand or to make sense of, it wouldn't help us at all. That is one thing that I believe. And so the other thing is like in the example of the Polyakov loop, we had exactly that problem. So it's like the formula looks more complicated, and we were looking for some ways to reduce the complexity, to decompose this equation in some sense, to get a smaller part of the equation that we interpret, and then we build it back together as this average over several lattice sides.
Okay. Maybe we take one last question from Frank. Frank, you want to ask?
Well, I'm not sure which one to ask. Well, maybe I guess maybe it's more important. Like, I guess we both asked about this speculation. Can you speculate, like, is it possible to find some other invariants from this method? Is it?
Yeah, so it's like, the interpretation procedure, or so let's start here. So it's like we chose to have only one neuron in the bottleneck. So that means we could only learn one scalar quantity. And it turned out that this scalar quantity was one component of the angular momentum. If you have more neurons here, then Siamese network can learn more or more difficult conserved quantities or invariants, or something that is not even physically interpretable. While you can learn more or more complicated quantities, it gets harder to interpret what is going on. So what you can do is like you can fix the angular momentum, which we did in the paper, and then it learns the energy conservation. But if you're not able to do that, and you want to learn more or more complicated quantities, you need to find a way to determine the optimal number of bottleneck neurons, and you need to be able to disentangle this representation. And this is normally quite hard, but it can be done, for example, through this L1 penalty and proper hyperparameter tuning.
Thanks.
Thanks. Also, Oleg, one more question, and maybe we stop.
Well, I have a related particular question concerning orbital motion about this invariant Laplace-Runge-Lenz vector. But as I understand, it is difficult, so it's necessary to have more neurons and so on. But this would be interesting.
Yeah, so we were aware of this vector, and this was also one of the quantities that we were looking for, but my question was that I'm not really sure. I think the Lenz-Runge Laplace vector is not an independent conserved quantity. Is it or is it not? I don't know it quite now.
In mechanics 101, you don't.
Well, it
use
can-
the angular momentum. So.
So and it depends. So if it's not an independent conserved quantity, then the neural network already stores the same information in the other conserved quantity, like the energy or the angular momentum.
Well,
But I do not know. So the question is it an independent quantity or not?
well, in a sense, I would say yes, because it's say the angular momentum is conserved for just it's due to rotational invariance, but this is just particular symmetry due to the motion in the central field. So this is in a sense it's not that regular as and for me this may be interesting problem because some regular symmetries just they are mostly known, but some symmetries which are not regular, which are occasional for this particular problem, this may be just general interesting problem for neural networks. Just it's naively thinking.
Yeah.
Okay, so let's thank Sebastian again.